start the second part of the webinar. We'll be talking about hospital powered by 5G. So let's first introduce ourselves. Mathieu, you want to start?
Sorry, you are muted. You're muted.
Mathieu, we can hear you. Okay, I think while Mathieu is reconnecting, I will start by introducing myself. So I'm Laurent Launay. I work in bcom Innovation Center in Rennes, and I'm responsible for the technology domain called applications, where we deal with medical technologies in bcom. And Mathieu is responsible for the network and security domain, and is where all the 5G developments are done in bcom. Nelly?
Nelly, yes. Good morning, everybody. I'm Nelly Besnard. I'm head of innovation department at Rennes University Hospital, and I will introduce a presentation focused on wireless operating room.
And our last presenter is Guillaume. Guillaume, we can't hear you. Okay.
Can you hear me? Yeah, can you hear me?
Yes, we can.
Okay. Okay, sorry, it's strange. Okay, so Guillaume Campion, I'm VP Product and Partnership for AMA. I'm currently joining by my phone because I'm currently having a microphone issue, but if you can hear me now, it's good. All right, so VP Product and Partnership for AMA, and be happy to present you what we're doing in this use case.
Thank you, Guillaume.
Can you hear me now, Laurent?
Yes, we can. So maybe
okay, great.
Resume your introduction, which I tried to do.
Sorry, everybody. So Mathieu Lagrange, I am in charge of the network and security department in bcom. So in that department, we are especially dealing with all the 5G aspects, especially for radio access networks and core networks. Thanks.
Thank you, Mathieu. So in this webinar, we'll be starting with the presentation of the medical and technical context regarding the hospital powered by 5G. We'll talk about the standards which are applicable in this project and that we will be using. Then we'll describe the use case that we are focusing on in the project. We'll talk about its architecture, the network architecture that's behind it, the KPIs, and we'll end the webinar with a short demo video that illustrates where we are with this project. So let's start with the medical introduction by Nelly.
Thank you, Laurent. So I will introduce some point of context and stress that from some years now, minimally invasive surgery techniques have been developing in hospitals. They significantly reduce the length of stay and recovery times for patients. But they are more complex and require new ways of viewing the operating seat, that is to say, inside the patient. Introduction of new technologies made this evolution possible. These technologies, however, are using a great deal of equipment. These include the contribution of intraoperative imaging and, more recently, the possibility of combining real-time video streams with augmented reality applications to provide an information to the surgeon that is more complete. All this has profoundly changed the working environment in operating theaters. As a result, a new logistical problems arise. With so many connection wires between the different equipment, asepsis could be a challenge, and freedom of movement for the staff may be compromised. In addition, modern operating theaters need flexibility of use, and this means that equipment need to be moved easily between rooms, and sometimes difficulties arise in connecting new equipment during an intervention. Next slide, please, Laurent. Therefore, we imagine a near future where a significant part of these connections will be able to be wireless and with a guarantee of flawless reliability. Indeed, these new technologies need flows with a very high throughput and an extremely low latency for perfect synchronization. In surgery, delay in image transmission could result in gestural deviation, which can have dramatic consequences. In addition, obviously, we must guarantee perfect security against any intrusion attempt via the network. Via wireless connection, we will also access more easily to remote expertise of our colleagues located in another city or even another country or continent. Likewise, the possibilities of transmitting images outside the operating room allow real-time adaptation of the operating program to the hazards of each procedure. Finally, yet importantly, it will renew the health training frameworks for doctors as well as other staff. The characteristics of 5G offer great perspectives, and with our partners involved in the 5G Tour project, we are working at the Rennes University Hospital to validate its potential, as will be explained in the minutes to come by Laurent, Mathieu, and Guillaume.
Thank you, Nelly. So let's talk now about some of the technical challenges. As you've seen from the introduction, the video plays a very important role in the OR, and it's also what requires the most bandwidth if we talk about data transmission. So the first challenge that we face when dealing with video in the OR is the interoperability. And we have to take into account the fact that most devices in current operating rooms rely on proprietary solution for video transmission. So they are not able to talk to each other. They are not compatible. So that's the first issue. The second issue, especially if we want to do augmented reality image fusion, it's very important to have the different video flows perfectly time synchronized. Because if we fuse two live images with some delay, it creates a misplacement in the image. So it can be a real problem for an intervention. So this time synchronization is critical. It's also critical if we deal with AI. For example, if we want to leverage the video and also signals coming from other equipments like anesthesia, doing a relevant AI processing requires the flows to be perfectly synchronized. And of course, the last application is if we want to record and replay multiple videos for training, for example, or to replay the intervention, to look at how it went afterwards. Also, the time synchronization is very important. And all these flows also require very low latency if we want them to be used during an actual intervention. The third and last challenge that we face is data management. We talked about video, but there are other signals which are very important in the OR, like the physiological signals coming from anesthesia equipment. It can be the 3D location of some of the sensors, some of the equipment that we need to obtain if we want to process them for augmented reality, or sometimes the parameters of the devices themselves, like the field of view or the information stating whether the endoscopy device is inside or outside the patient. These are very important parameters if we want features like dynamic layouts. For example, if we want to display the best layout for the physician, we have to transport those information as well. So these are what we call metadata in this project. So the first standard that we decided to use in this project is Daikomartv. Daikomartv is a standard which is recent. It was approved in November 2019. It was initially developed and proposed by bcom to the DICOM standard committee before it became an actual standard. So this results from the fusion of two existing standards. Daikomartv is for real-time video. So the first standard that it leverages is a video standard called SMPTE ST2110, which is used for broadcast and to deal with real-time video. And on top of SMPTE ST2110, we added DICOM, which is a very well-known standard for medical imaging, very well adopted by the community and the industry today. So we added a DICOM component to SMPTE ST2110 to create this new standard for DICOM real-time video. So if we look a little deeper, the way it works is the data coming from the equipment travels through different essences, channels, which we call essences. So of course the video is one. The audio can be a separate essence. And there is also a dedicated essence for the metadata that we just talked about. Everything which is important, but which is not video. And all these essences are time synchronized. They are time stamped thanks to the use of a master clock. And this is the way this information travels into IP. So this is the standard that we decided to use for this project. So Mathieu will now talk about the 5G aspects of the standard.
Yeah, thank you. Thank you. And which is in GP. Which has been implemented finding networks to support medical agents. That has been done as part of the call. Explain a bit the process. GP a kind of very huge organization. The process is a bit small. In GP, there is 3 stages in terms of writing specs. The first one is stage 1, and it is taken in charge by a group that is called A1 group, and that group is in charge of translating, let's say, vertical requirements, customer requirements into technical requirements and service definition. And then there is the stage 2, which is the architecture work, I would say, that is also taken in charge by other groups, SA groups. And then the stage 3, which are actually the detailed specifications, all the very detailed technical work, detailed protocol definition, etc. That is written by CT and RAN groups. And where we are for medical applications in 5G is we are at the stage 1. The feasibility study has been completed by the end of 2020, and the normative requirements as well has been written and integrated into 3GPP specs by the end of 2020 as well. You can refer, if you're interested in that work, to a number of documents. There is this TR 22826, which collect and gather all the different use cases that have been covered by that work, and all the you have also interesting documents as 2261, 22104, and 22263 as well that have interesting things as well. Just to mention it, that work has not been done by bcom alone. We have been supported by other companies like KT, Orange, Sharp, LG Electronics, Philips, Huawei, Siemens, Vodafone, and they have all contributed to that work as well. Thanks. Next one, Laurent.
Yes, thank you, Mathieu. So let's now talk about the use case that we are considering into this project. So for the wireless operating room, we wanted to demonstrate what private 5G network can bring in terms of benefits for a situation requiring a very low latency and a very important amount of video data to be transferred. So we wanted to stress the latency and the bandwidth during this type of use case. So we focused on a scenario that simulates a very specific type of intervention, a cardiac intervention. So that can be, for example, an intervention such as a mitral valve replacement. So it's a complex intervention which requires 2 live video streams. The first one is echography, ultrasound, which is used to display the cardiac cavities during the procedures. And the second one is X-ray imaging, which is the main source of information used by the cardiologist to understand where he is, where the devices here are, and also to look at the coronaries. So these 2 informations are complementary. So more and more now, what we display to the physician is an augmented reality view that merges these 2 live images into a single one, so that he doesn't have to look at 2 images at the same time. So this is a scenario that we're talking about. And also we added in this scenario the fact that the cardiologist is wearing smart glasses, and we'll talk a little more about that later on, so that he can stream his view to a remote colleague. So that's what we call e-proctoring. And then the scenario also includes an external camera, typically a sailing camera, which captured the view of the OR so that it can be transmitted to a different location, such as a training theater, for example. So for this scenario, we decided to use a specific operating room located in Rennes University Hospital. It's called TerraImage. It's an actual clinical room used for intervention, and half of the use of the room is also for research. So just a few words about the overall architecture that we use for this use case. So as you can see on the left, we have the different equipment that produce data in the scenario: the ultrasound imaging device, the X-ray imaging, the camera, which is used for the localization. We will also describe it a little more, the smart glasses, and the display at the end for the augmented reality application. So the live imaging flows are first converted to DICOM-RTV and being transmitted to a processing device, which sends back the result to the augmented reality display. So for this scenario, we have not used 5G everywhere because wireless is not important for all equipment. For example, the X-ray imaging device is fixed, so wires are not a big issue for the X-ray device. Wires are an issue for ultrasound because it's usually it's supposed to be mobile. You can move the ultrasound machine from one room to the other. So the fact that you don't have to reconnect it to the screen of the room can be a big advantage. And of course, it's obvious that the smart glasses have to be wireless as well. So the 2 uplink connections that we used, for which we use 5G in this use case, are the ultrasound and the smart glasses. And then what we will be working on, which is not implemented yet, is the downlink connection, which sends the result of the augmented reality processing up to the screen that is used by the surgeon. So the augmented reality application architecture, without going into too much details, is described here. So we'll be using a specific dynamic cardiac phantom. So it's dynamic because you can simulate flow. You can inject actual flow, water, into the phantom to show simulate the blood inside the arteries and the heart cavities. And this phantom is compatible with both ultrasound and X-ray imaging. So for ultrasound, we'll be using a specific 3D marker attached on the probe. This 3D marker will be used by a 3D camera in order to locate in space the probe, so that we know exactly where the live ultrasound image is acquired in the 3D space of the operating room. And for the X-ray part, so we'll assume the C-arm, the X-ray component of the cath lab, is at a fixed position, which is common during an intervention. And we'll calibrate the location of this C-arm in the same space as the one used for the ultrasound image, so that the live X-ray image and ultrasound can be combined and show the type of view that we see here on the right, which mixes the information from the two imaging devices and shows the complementary information. So we can see the device like the catheter or the device that will be placed during the procedure, thanks to the X-ray. And thanks to the ultrasound, you can see the heart cavities, like the muscle of the left ventricle, which is not really visible usually on X-ray. So these two, the fusion of these two flows is what we call the augmented reality application in this use case. So we'll now talk about the architecture for the smart glasses solution that we mentioned. So I let Guillaume.
Yes, thank you, Laurent. Can you hear me well? Okay. Okay. So, so AMA, we are, as Laurent said, we are coming up with a smart glass solution. Behind it, it's not only smart glass; it's a full remote assistance solution. We currently have we work on hospitals and medical care for a couple of years now, with a specific focus on emergency services. We have already a couple of French emergency services already using our system. So we are fully following European rules such as GDPR and as well medical track records. This being said, what was important here, it was to bring our service on a closed network. So that's what we have done, bringing this our WebRTC solution. So WebRTC is a video conferencing standard, web-based, so you only need web browser. We deployed this full service within bcom premises, so everything on a closed network, so that will be able to study the 5G capabilities and constraints. So this being said, even though we have a specific focus on emergency, we did have something special. If you can, Laurent, switch to next slide. We did have one specific one, which is more for educational purposes. So here we're using a smart glass, still using our remote assistance solution with our WebRTC technology behind it. Here, the cardiologist, as you can see on the left, he's wearing smart glasses. The smart glass is actually recording and transmitting and broadcasting a first-person video. So he shows what he's currently seeing with his eyes, because it's the same line of sight as his eyes. And there's a display screen as well within this smart glass. So here's the main use case out of this use case 8 is e-proctoring, meaning that here the cardiologist is actually showing what he's doing to one of his colleagues, either to get to train him or to show him to get new advices. Could be another doctor, another specialty. So on the right hand, you can see another doctor actually seeing in real time what's happening, and the doctor not only being able to share his video, he does a full video conferencing, so he can speak its voice as well. And remotely, the doctor here on the right can actually take pictures and push it as well on the smart glass display screen, because both have both a microphone and a display screen. So here, what we wanted is to use this full hands-free solution. So this is one of the most important, is that to keep free, so the surgeon here can still work and use the probes, is to be able to share his first-person vision, because this is the best vision to actually share his knowledge and point of view. So here we're plugging this smart glasses to a 5G phone and get it connected through this 5G antenna, which is within the Terra Image operating room. So this here, just to summarize, what we have done is currently bringing a full dedicated hardware with a full software solution for video conferencing and video and remote assistance on both sides, so to bring the best value and proposition for e-proctoring, meaning to give the best help between a surgeon and a remote doctor colleague who actually will be able to share both knowledge in both ways. Okay, Laurent.
This is Mathieu. Yeah, I will say a few words about the network architecture, the network setup to support the different use cases. We've been talking about the use case 8 and the one operating room, but actually the network that is being set up in France will support as well the use case 7, the one with the ambulance and the remote interventional support to a physician inside the ambulance for a ultrasound examination. So in that setup, we have 3 main sites that are connected together through a VPN connection. You have one site in Paris that is in Orange, actually, another one which is the bcom premises, and the last one is actually the Rennes hospital in Rennes, and the technical room close to the operating room. So the network setup is as follow. You have an orchestration node in Paris, which is based on ONAP, and that is in charge of actually deploying on demand all the network functionalities that are necessary to implement the different use cases. Then this orchestrator will deploy, instantiate a core network that is a core network provided by bcom. So the control plane will be deployed into a Kubernetes cluster in bcom data center in Rennes. It will be in charge of actually managing the mobility, managing the security as well, and establishing and controlling the different sessions involved in the different use cases. And then bcom also provide 2 UPF. So for the data plane, one is will be deployed in OpenStack cluster in bcom premises in Rennes, and the other one will be deployed as a physical network function in the technical room close to the Terra Image operating room, so in Rennes hospital. And finally, you have 2 radio access networks, one in bcom premises for the ambulance use case provided by Nokia, and a similar one also in the operating room to support the use case 8. Those 2 radio access networks are implemented support, let's say, FR2, what we call FR2, which are actually the millimeter waves band in the 26 gigahertz spectrum. We will be operating into 400 megahertz bandwidth to support the capacity that is required, especially for, we will see that later on, required for the use cases in the operating room. And so for time being, we will be supporting non-standalone mode. So we have also a 4G cell that will be used to establish the different sessions in the band 38. But we hope being able to move to a standalone mode. So we full 5G NR and only 5G NR, I would say, as a radio access network for before the end of the project. Next one, Laurent. Yeah, on that slide, I would like to talk briefly about the relationship with another European project, which is 5G Eve. As you may know, 5G through on 5G network infrastructure, especially the three main nodes, three main sites I was talking about before, are basically inherited from 5G work, and especially 5G to service layer, leverage on 5G Eve portal and 5G Eve interworking, as you can see on the picture. To service requirement for we'll also rely on 5G Eve monitoring capabilities, so especially the different functionalities that are needed for collecting, monitoring the data for the entire vertical service. Whenever all the different network functions developed for 5G2 will be supporting the required extensions for actually publishing those monitoring data into the 5G monitoring platform. However, in the first phase of the project, first phase of 5G tour, we will bypass the 5G portal and the 5G tour talk directly to that orchestrate. And we'll use that portal only in the second phase of the project. Next one, Laurent. And for the next slide, so it's a brief summary of different KPIs, technical targets, technical objective we have on that project. So the so far, especially for the use case 8, the one in the operating room, the one with the augmented reality application. So one of the key requirements is, of course, the latency requirements. The one you see here is end-to-end latency between the generation of the image by the medical equipment, so the ultrasound probe, for instance, and the display of that very same image augmented on the monitor in the operating room. So that's really round trip time that includes the application processing time, the potential compression and synchronization time, and then also the transportation of that of the data through the 5G network. So it means there is approximately something like 70 milliseconds each way in terms of latency, and for the transportation time through the 5G network, it translates into something like 15 milliseconds for the radio access network and for the UPF as well. That requirement is really key because actually it translates also into something like a geometrical error for the instrument location inside the patient body. So if we have very long latency, potentially it can result into serious injuries for the patient. And also it results into a more complicated operation for the surgeon. So the longer the latency, the more complicated the surgery is. So we really want to have that latency as short as possible. Then the second parameter, the jitter, is also very important because, as Laurent explained before, all the different imaging equipment for that use case are all synchronized into the same master clock. And that synchronization is achieved through a PTP protocol, which is 1588 v2, if I'm correct. So that means we have PTP messages that are exchanged over 5G connection, and that synchronization protocol will work only well only if we have a very stable jitter for that 5G connection. The other parameters, like especially the capacity, the bit rate, I would say, of 3 gigabits per second are required to transport the different video data. You have to know that in general, the physicians, the surgeons, they are kind of reluctant to have to use I would say compressed video. So if we want to have HD video with 60 frames per second, which is not compressed, we need to support 3 gigabits. in terms of aggregated bitrate at the cell level. We would need to have the same, symmetrical bit capacity in uplink and downlink, since we also need to stream the video stream up to the augmented reality application at the edge also. But we have some limitation for time being in the radio access network, which means that we will have to compress the video in the uplink. So for time being, the requirement in the uplink is 100 megabits per second. We try to improve if possible throughout the lifetime of the project. And then the last two requirements are reliability and availability, of course, which are key for medical applications. I'm not sure we will be able to generate the required metrics and verify that these two figures are met in the project, but this would be needed in a real operational setup in case of the deployment of 5G connection in an operating room. Those are the figures that have been specified as well in 3GPP specs. So you can refer to those specs to understand the rationale behind those numbers. Thanks.
Thank you, Mathieu. So to conclude this webinar, we wanted to share a quick video. So let me do that right now. So as you will see, the video is not, it shows an experimentation which is not done in Rennes University Hospital yet, because we could not access the room due to the pandemic. So we did an experiment in the lab. And since we didn't have access to a live X-ray imaging system, obviously, we used a video camera instead. So the augmented reality application that we have implemented in this demo is consists in augmenting the video flow from this video camera with the ultrasound, so that we can see the location of the ultrasound plane on top of the video itself. So let me just play it. I think I should change the setting. Just give me 1 second to do that. To optimize for video. Okay.
It does not start for time being. No.
Sorry.
Unless this is only me, but I cannot see your video.
No, we cannot see the video.
Oh, okay. Let me try again.
It is written that you are starting to share, but nothing happens.
Okay. I'll try again. The WebEx is telling me that I am sharing, so that's strange. Can you see it?
Not yet.
Not yet.
Do you want me to try, Laurent?
Yes, maybe, since it doesn't seem to be working. Sorry about that. Go ahead, Mathieu.
Medical interventions are more and more complex and involves multi-imaging devices. Wire may represent a risk for the team, defocused from the patient. They also prevent to easily move the devices from one room to another. Then, the use of 5G inside the operating room offers a great promise to remove unnecessarily wires. We can then transmit the signal in a fast and secure way without any wire.
This experimental setup was designed to show the technical feasibility of using 5G to transmit signals from multiple devices during an intervention. A cardiologist is using an augmented reality application relying on 2 imaging devices while wearing smart glasses to share his view with a remote expert. All 3 real-time video signals will be transmitted to the processing devices using a single private 5G infrastructure. The first signal is ultrasound imaging, a special 3D printed marker attached to the probe and tracked by a RGBD camera allows to know its location in space at all times. The second signal is from an external camera filming the probe and the patient. Both video flows are converted to Daikomartv standard prior to their transmission to the processing device. Registration and fusion are performed by the augmented reality application to produce the display used by the cardiologist. The third signal is from the AMA smart glasses. Thanks to a 5G smartphone connected to the glasses, it is transmitted to a local edge server, then sent to both a remote display located in CHU facilities and to a control screen in the room. The 5G network leverages on bcom's core network solution deployed in bcom data center. In order to reduce the end-to-end latency, the data plane carrying the data from the 2 imaging equipments to the AR application is instantiated in Edge Cloud. Note that the applications, the collaboration tools from AMA and the AR application from bcom, are also hosted in the same Edge Cloud.
So, thank you. So we will, I'm not sure.
Thank you, Mathieu.
Okay, thank you, Laurent. We can take any question you may have on that work. We will be happy to answer.
If you want, you can write the questions in the chat. So if nobody has any questions, so we can close the session. We would like to tell thank you to all of you for the participation in this event. Thank you for this fruitful presentation. It was very interesting, really. And I would like to wish good luck to all of you, and we will wait for you on the next webinar sessions. And we hope that we will organize them in the future. So thank you all.
Thank
And
you,
now
Laurent.
we are ready